problem, there is a point charge with magnitude Q. We're going to assume it's positive because it doesn't say otherwise, inside the cavity of a conducting shell with net charge 2Q. So this is a conductor. The charge on the conductor is Q of the conductor equals 2Q. The question is, what are the induced charges on the inner and outer surfaces of the shell? So what is the charge right here on the inner surface, and what is the charge right here on the outer surface? And we know there will be charges on the inner and outer surfaces because in a conductor, when we put it in an electric field, the charges will separate in order to create a net field of 0 inside the conductor. So we're going to use our Gauss's law that says that the integral of the electric field over a Gaussian surface is Q inside the Gaussian surface divided by epsilon naught. That means we have to select a Gaussian surface. For the Gaussian surface, we'll draw a sphere inside of our conductor. The reason we pick a sphere inside the conductor is because we know the electric field inside the conductor is 0. So our electric field is 0, so the integral of E dot dA, the net flux, is going to be 0. Tells us that the net charge inside our Gaussian surface, inside the dotted line, equals 0. The other thing we know about our net charge is it has to be the total charge that's inside this dotted line, so it would be the point charge Q plus whatever charge is on the inner surface, Qi. So Q plus Qi equals 0, so our Qi equals minus Q. So the amount of charge drawn to this inner surface is the negative of the value of the point charge, which is in the cavity. So that's our Q inside. What about the Q outside? So let's think about the conducting shell itself. First of all, we're given that the total charge is, the Q of the conductor is 2Q. So total charge equals Q of the conductor equals 2Q. Whoops, 2Q, and that was given. We also know that the total charge, whatever it is, would have to be whatever is on the outer surface plus whatever is on the inner surface. So Q of the inside plus Q of the outside. These are both the total charge. So 2Q, the total charge which is given, equals the charge that's on the inner and on the outer. So the total charge is split up between the inner and outer surfaces. We know Qi, that was minus Q, we found that in the first part, plus Q on the outer surface. So now we'll solve for Q on the outer surface. 2Q minus Q gives us 3Q. So that's the amount of charge that's on the outer surface. The last part is to sketch the electric field. So inside here, the electric field is due to the point charge. We know that electric field will point away from a positive. So we'll draw our lines going outwards. The electric field inside the conductor is 0 because electric field inside a conductor is always 0. Okay, so that line just got a little bit astray there. Let's just make sure we draw that evenly. Should come up this way. So for the electric field outside, let's draw a Gaussian surface out here. And let's think about our Gauss's law out here. So out here, the net electric flux, E dot dA, equals Q inside over epsilon naught. The net charge inside is the Q on the conductor plus the point charge Q, so that's going to be 3Q over epsilon naught. We know that the integral of E dot dA will work out to be E times 4 pi r squared equals 3Q over epsilon naught. So E is equal to 1 over 4 pi epsilon naught times 3Q over r squared. So the electric field, once we're outside the conductor, is the same as the electric field due to a point charge with a magnitude of 3Q. So what that tells us is that the electric field lines will point outwards. This charge is 3 times as big as the point charge, so there will be 3 times as many lines. So it will look something like this. So there's the electric field at all the spaces in that region.